find yours, take it. If you don't, I'll get them back to me, and I'll keep doing analysis. So last time we started talking about limits, and let me remind you what limits are. We talked about the meaning of this phrase, the limit of the function as the argument goes to a being equal to some number. And the mean was f of x gets arbitrarily close to L as x approaches. And the picture may be something like this. You have a point A on your graph, and the function as the argument approaches this point A comes closer and closer to some value of L. Maybe something like this. And it also should approach the same value from the other side. Maybe something like this. So as x approaches A, the function approaches this value L from both sides. And at the point A itself, it doesn't matter how the function is defined. It might be defined by this value L, it might be defined by some, maybe it's not even defined at this point, maybe it's defined by some extra value L, it doesn't matter. So the value of the function at the point A doesn't matter to the purpose of limits. What matters is how the function behaves near the point A as the argument approaches. So I want to start with the question about limit. Let's compute such a limit. Limit is x equals to 2. Squared minus 3x plus 2 divided by x squared minus x plus a minus. And let me give this question to you to think first. So think about this question, and I'll give you some options for the answer. And if you have an iClicker, and if I manage to set this thing up, please give the answer. This thing is not working yet. So it will. Alright, so now it is working, and now you can express your opinion about this question. Alright, so now I can discuss it with your neighbor for another minute.
What do you guys think? I think it's D because as the both approach 0, so you can cancel out x squared, and then as 3 is getting okay, so you take the derivative of both top and bottom, so you get 2x minus 3 over x minus 1. And so as these approach 0, they become 0, so it's negative 3 over negative 1.
Can you just go into x, x minus 2, and then x minus 1 on top, and below the x minus 2 bracket, x minus plus 1.
You mean
yeah,
you factor it?
Yeah, exactly. Factor it and simplify that. And then x minus 2 is cancelled, and then you have those two things left.
Alright,
Yeah.
so let's discuss the question together.
Yeah, so it's
first
still
of all,
good.
you look at this expression and you try to argue in the most naive possible way. Sometimes it just works. So the naive ways, if the argument x is close to the point 2, so x is 2 point something or 1.9999. What happens to the numerator? Well, x squared is going to be close to the 4, to the number 4. Then x squared minus 3x is going to be close to 2 squared minus 8 times 2, so minus 2. And then you add 2, so you get a number which is close to 0. So the numerator is going to be close to 0. So we get a number close to 0 in numerator. What about denominator? Well, 2 squared minus 2 and minus another 2 is also close to 0. So you get a quotient of two numbers which are close to 0. Right here I wrote something like 0 divided by 0. Of course, this is not the value of the limit. There is no such thing as 0 divided by 0. What this stands for is just kind of in our head, we think about what happens to numerator, number close to 0. What happens to denominator, number close to 0. Do we know what the quotient is? No, we have no idea. Because if you have, let's say, the numerator was something like 0.1 and denominator was something like 0.001, the quotient is going to be 100. If you slope it the other way around, the quotient is going to be 0.01. So you really don't know what the quotient of two small numbers is. So this thing is undefined. Well, but the limit is not quite about the value of the function at the point 2. It's about what happens when the function is x gets close to 2. And apparently we have to make a more careful argument. So let's look at this thing. So we argue that both numerator and denominator are close to 0 as x is close to 2. Well, this thing is close to 0 and x is close to 2. What is the reason? The algebraic reason for this is, well, out of this expression, we can factor out an expression which is x minus 2. That makes this expression close to 0 and x is close to 2. So I already know not only that this expression can be factored, I also know one of the factors. It must be x minus 2. That's the thing which gets close to 0 as x is close to 2. And then I'm going to have some other factor. So I look at this thing. If I try to factor x minus 2, well, minus 2 times something should be plus 2. So it should be minus 1. And I can check. It's x squared minus 2x and minus another x, yes, minus 2 times minus 1 is plus 2. So it works. Same argument applies to denominator. It is 0 when x is equal to 2, so it must be divisible by x minus 2. I will factor out this x minus 2 factor, and I will be left with x, well, what should I write here? Plus 1, yes. So now I have minus 2 times something is minus 2, so this something is plus 1. And once again, to be safe, it's better to check. X times x is x squared, minus 2x and plus x equals minus 1x, minus 2 times 1, minus 2. Okay, it works. Now, I will use that x is not quite 2. If x were exactly 2, I would have a problem. I would have 0 in numerator, 0 in denominator. But for calculation of the limit, it doesn't matter, well, yes, it doesn't matter what the value of the function is at point. Only for nearby values, 2.001, 1.9999. So these values matter. So when x is close to 2 but not quite 2, I can cancel these things out. And now I can try to argue in the most main way. When x is close to 2, the numerator is close to 2 minus 1, which is 1. The denominator is close to 2 plus 1, which is 2. So that's the answer, 1 there. And I think most of it was right. Okay, so questions about this thing? You had a chance to think about it, now you see the solution, so maybe any questions? Alright, then let's talk about a similar question but with a quite different answer. Let's another exercise, for example, as x approaches 2 of s divided by x squared minus x minus 2. Same denominator, why different numerator? So what can we say about this thing? So the first step when you look at any question about limits is to try the simplest possible approach. And the simplest one is what we did here. Try to argue what happens to the numerator when x goes close to 2, what happens to the denominator. The numerator becomes close to 2. The denominator comes close to 2 squared minus 2 and minus another 2, which is 0. Well, once again, this is not the value of the limit, it's just our way of thinking about it. So the numerator is close to 2, the denominator is close to 0. What can we say about this expression? Well, first of all, it's not defined. You cannot really divide 2 by 0. But unlike this expression, which was a shorthand for a quotient of 2 small numbers, the quotient of 2 small numbers can be actually close to some particular value. So for example, here, it turned out that the numerator was about 1/3 of the denominator. So if the numerator is 0.1, the denominator must be 0.3, close to it. If the numerator is close to 0.01, the denominator was close to 0.03. And the quotient turned out to be close to some particular number, 1/3. With this expression, it's actually not possible. If you try to divide 2 by some really, really small number, what are you going to get? something really large. So if you think about dividing 2 by, say, 0.1, you get 20. You divide 2 by 0.0001, you get 2 and 4 zeros. You divide 2 by 0.1001, you get 2 and 10 zeros. So you get really, really large numbers. Also, if you divide, well, I told you the denominator is close to 0. I didn't tell you whether it's positive or negative. It doesn't matter. Even if you divide 2 by negative small number, think about minus 0.001. You are still going to get huge numbers, but now they will be negative. So 2 divided by minus 0.001 is minus 2000. So this expression, there is just no way that it's going to be a finite number. You can't divide a number close to 2 by a small number and get something which is close to some finite number. This thing becomes arbitrarily large. So without even continuing, without factoring, without doing anything, I know that this limit does not exist. And the reason is, well, the function becomes arbitrarily large. As x approaches the point 2. Once again, the reason for this, as x approaches 2, the denominator approaches 0, but the numerator approaches some finite value, 2. And if you divide 2 by some increasingly small numbers, you're going to get increasingly large numbers. Maybe negative, but still large. So this limit just cannot exist. Yeah?
Why wouldn't it be infinity?
So we'll get to the discussion of infinity or negative infinity. So for now, we'll just write about any limit which is not a number, that doesn't exist. Later in the course, we'll have a little bit finer distinction of the limit being infinite or minus infinite or actually not existing. In this particular case, well, it happens that it actually does not exist. I'll explain in a second on the graph. But for now, even if it's infinite, we'll just write that it doesn't exist, which means does not exist as a number. Yeah, another question here? Yeah.
If the limit is not exist, then I'm a little bit confused about how it becomes arbitrarily large as x approaches 2.
Okay, so think about, I won't actually compute anything here. Think about what would be the sequence of numbers which would compute if you plug in values which are increasingly close to 2. So I'll plug in x, and I'll compute f of x divided by x squared minus x minus 1. So to make it up completely, I don't want to use an initial calculator, I just want you to get the spirit of what happens. So I will be plugging in 2.0, 2.001, 2.00001. And maybe 1.9999. So what's going to happen is when x is close to 2.22, the denominator is going to be close to 0. I'm not sure what it is exactly. Let's say it was for this value of x, let's say 0.1. And the numerator, let's say it turned out to be, well, it should be close to 2, so let's say it's close to 2.1. It's actually 2.1. The quotient is going to be something like 21. So I'm not saying that it's exactly this, but the order of magnitude of this number. If I plug in x, which is even closer to 2, the denominator is going to get even closer to the point 0. So it's going to be even smaller. The quotient, the numerator is still 2. The quotient is going to be, let's say something like this. The next one is going to be even larger. Something of the order of 200,000. Even if you plug in numbers which are close to 2 but smaller than 2, you'll get answers which are large, but this time negative. These values do not approach any number. So for a limit to exist, we must have the following. As x approaches the number 2 from either side, the function approaches some number. What number these values approach? Well, no number. So they become larger and larger and larger. And we see that it's in such kind of table, these numbers do not approach any finite limit. We say that the limit does not exist. Let's also look at the picture. I'll compare the picture for this function with the picture for this function. So sketch graph. This one will be for the function x squared minus 3x plus 2 divided by x squared minus x plus 2. So we know that this function is basically the same as this function, x minus 1 divided by x plus 1. Well, I won't talk about how to sketch a really good graph of this function. But the answer happens to be like this. It's so it turns out that the graph of this function is somewhat like this. Except at one point, when x is equal to 2 exactly, the original function is not defined, but this function which I drew here is defined. So to make it actually a graph of this thing, I will eliminate the point 2 from the graph. And in this computation, what we found was as x gets closer and closer to 2, the function gets closer and closer to the value which it kind of supposed to have at this point. It was supposed to have at this point, which is 1/3. So here, even though the function itself is not defined at the point 2, it's going to be, well, it is close to the point 2 when x is close to 2. So the function is close to 1/3. When x is close to 2. Now let's look at this function. X divided by x squared minus x minus 2 as a function of x. This one is even more complicated. So it looks somewhat like this. There is point 1, there is point 2, and the function like this. So that's the graph. It consists of 3 parts, one like this, one like this, and one like this, and these are points 1 and 2. At points 1 and 2, the function is not defined because the denominator becomes 0. Well, this function was also not defined at the point 2, but it wasn't a problem for the limit. Here, it is a problem for the limit. When x approaches 2, let's say from the right, the function becomes increasingly large and positive. It goes all the way up. It does not approach any finite value. If x approaches 2 from the other side, the function escapes down. It does not approach any number, it escapes, well, in this direction, to infinity, somewhere far, far away. So this picture is really, really different from that picture. Here, the function for both sides approaches the same number. Here, it doesn't. From either side, it escapes to infinity. And, well, from this picture, you can also see why I don't want to write that this limit is infinity. I want to say that it just doesn't exist. The reason is, well, from one side it escapes to positive infinity, but from the other side it escapes to minus infinity. So we'll get to talk about it later, but for now we'll just say the limit does not exist. Okay, so questions about this? Example. Okay, so now we basically know how to compute limits. So we know how to compute limits of So when I say polynomial, I mean just something like this. X squared times some number, maybe x cubed times some number, pluses or minuses in between. So an expression of this kind. So sum of powers of x with some coefficients. And we just discussed how to compute these limits. If the denominator is not 0 at the point A, there's no problem. Is P of A divided by Q of A. So if you know that as x approaches A, the denominator approaches a non-zero number, the whole quotient, well, the numerator approaches P of A, the denominator approaches Q of A, the quotient approaches the quotient P of A divided by Q of A, no problem. If the denominator is not 0 at this point. If Q of A is equal to 0, we have two cases. One case, if the numerator does not approach 0, like in this case, then we are trying to divide a non-zero number, non-zero finite number, by something which gets increasingly small. And the function escapes to infinity or negative infinity. So we say the limit does not exist. In the other case, if the numerator also approaches 0, then we have this situation of a quotient of two small numbers. A priori, we don't know what happens. You might be in whatever situation. The limit might not exist. It might be infinity, might be a finite number, whatever. But we know what to do. We know how to find out. Factor out x minus a from p to q. Cancel it out. So we have a trick how we will deal with such a thing. If both numerator and denominator approach 0 when x is close to a, it means that both are divisible by x minus a. Factor it out, cancel out x minus a, and you are going to get a simpler thing. Alright, so this is what happens when the functions which you are computing the limit are what's called rational functions, functions of two polynomials. Unfortunately, not all functions are functions of two polynomials. So let's talk about next example. So it's not an example of this thing, it's under view together, so it's only one side of the limits. So let's talk about the limit of x to value of x divided by x when x approaches 0. So first of all, it's not the kind of question that we already talked about. Absolute value of x is not a polynomial. It's not just sum of powers of x numbers. It's absolute value which spoils everything. Well, what exactly does it spoil? What exactly goes wrong with this thing? Well, let's look at this expression. Remember that absolute value of x is just the number x, but without the sign. It's always positive. Regardless of whether x is positive or negative, absolute value is always positive. Okay, so if I want to understand how this expression behaves, I better separate two cases. One when x is positive, another one when x is negative. Okay, so what happens when x is positive? What can I say about this quotient? Absolute value of x divided by x. What is absolute value of x when x is positive? Yes, so when x is positive, absolute value does nothing. X is already positive, so applying absolute value doesn't change it. So when x is positive, this expression is just x over x, which is just 1. When x is negative, what happens to absolute value of x over x? This might be a little bit more tricky. Negative 1, right. So think about something like -5. Applying my absolute value to -5 removes the minus sign, so you have just 5 in numerator, but in denominator you still have -1. The quotient is going to be -1. In other words, absolute value of x when x is negative is the same as minus x. So it's the same x, but you have to remove this minus sign by multiplying with the -1. And then the quotient is -1. Okay. At the point 0, the function is not defined. For x equal to 0, absolute value of x over x is not defined. Well, for computation of limit, this information is absolutely irrelevant. I don't care what the value of the function is at the point 0. But this is very relevant. X approaches 0. I didn't tell how it approaches 0. I didn't tell whether it approaches from the positive side or from the negative side. It could be plus 0.0001 or minus 0.0001. But that creates a problem for the limit. Because when x is positive and small, the function is 1. When x is negative and small, the function is -1. So if I were to use such a table, I would have a funny situation. So let me actually sketch how such a table would look like. I plug in 0.1, the answer is 1. Plug in 0.001, the answer is 1. Plug in, the answer is 1. Well, I start getting happy, maybe the answer is actually 1. I look at the sequence of numbers, of course they approach something, they approach 1. But then I try some negative value. Minus 0.1, the answer is -1. Minus 0.001, the answer is -1. Minus 0.000001, the answer is -1. So unfortunately, I don't have a convergence. On one side I get 1, on the other side I get minus 1. So I'm forced to say that this limit does not exist as well. I can't say that it's two different numbers, 1 and minus 1. I must give some number. Which one? Is it 1 or minus 1? Well, you can't tell. The limit does not exist. The function, if you sketch the graph, set value of x divided by x, looks like this. It's plus 1 when x is positive, it's minus 1 when x is negative, at 0 it's not defined, so no value at the point 0. And when x approaches 0, well, from one side the function approaches 1, from another side it approaches minus 1. So overall it doesn't approach anything. But now it feels just wrong. I mean, yes, it is mathematically the correct answer. The limit doesn't exist, the function doesn't approach any value, but it feels wrong. When I say that this function doesn't approach any value, I kind of lose this information that from one side it approaches one value, from another side it approaches a different value. And the reason the function overall doesn't approach anything is because these two values are different. Well, for this reason, we introduce new notation. So new concept. I'll start with this example. So in this case, I will have two what are called one-sided limits. A one-sided limit is about what happens to the function as x approaches the limit point, but only from one side. In this example, I'll have two limits like this. X approaches 0, and we say it from the right, and the notation is x approaches 0 plus, in this order, 0 and then plus. So when x approaches 0 from the positive side, from the side of positive numbers, the function approaches 1. When x approaches 0 from the side of negative numbers, so if x is minus 0.00001, the function approaches minus 1. And overall the limit as x approaches 0, well, does not exist. So let me give a more formal definition. We say that limit as x approaches some value from the right, and the notation is x approaches a plus our function is equal to some number if f of x gets arbitrarily close L as x approaches a, staying larger than m. So this is the concept of one-sided limit. For limit itself, we allow it to approach a from either side, either a little bit larger than a or a little bit smaller. For a one-sided limit like this, say limit from the right, limit as x approaches a from the positive side, it means that x is very close to a, but a little bit larger. We don't allow it to get smaller than a. And similarly, the limit as x approaches a from negative side, from the left, f of x is equal to some number, if f of x approaches L as x approaches a and stays smaller than a. So now we have a way to express this knowledge. This function, let's say this function, this is value of x over x, when x is slightly larger than 0, is very close to 1. This particular function is actually equal to 1, it doesn't matter. It gets close to 1. When x is close to 0 but is negative, the function is close to minus 1. So let's have some other examples. Before these questions about this concept, one-sided limit. Okay, so let's talk about some other examples. Or maybe before an actual example, a picture. So a typical picture here would be something like this. As x approaches a from one side, the function approaches one number. From another side, the function might approach a different number. Let's say this is L1, and this is L2. And in this case, L1 will be the limit of f of x as x approaches a from the left, so close to a, but a little bit smaller. And L2 is the limit of the function as x approaches a from the right. Approaches a, but is a little bit larger. And once again, the value at the point a doesn't matter at all. It can be anywhere. Maybe here. Doesn't matter. So now let's have an example. Function is going to be one of those functions which is defined by cases. So it's going to be x squared when x is greater than minus 1 and x equal to x minus 2 when x is smaller than minus 1. And the question is, what is the limit of f of x as x approaches minus 1? The question is not even about one-sided limits, it's just about the limit. What happens when to the function x approaches minus 1? To argue about what happens to this function when x approaches minus 1, I'll have to consider two cases. Actually, make things. So it's really defined for minus 1. So I'll have to consider two cases. X might approach minus 1 but stay a little bit larger, and it can approach minus 1 and stay a little bit smaller. The reason I have to consider these two cases is because the function is defined by two quite different formulas in these two cases. When x is larger than minus 1, the function is x squared. When x is smaller than minus 1, the function is this, absolute value of x minus 2. So I'm forced to consider not just the overall limit, but two one-sided limits. What happens to the function as x approaches minus 1 from the left and from the right. So let's do it. start with one-sided limits. I'll compute what happens to the function as x approaches -1, let's say from the right. I'll start with this one. When x is close to -1, but a little bit larger, the function is defined by which formula? The first one or the second one? So x is close to -1, but a little bit larger. Which formula should I use? First one or second one? First one, yes. So x is larger than -1. I'm using the first formula. But this limit is really simple. When x is close to -1, regardless of whether it's larger or smaller, x squared is close to 1. So this one-sided limit is equal to 1. Okay, what about the other side? Limit of the function as x approaches -1 from the negative side. The notation is a little bit strange. X approaches -1 minus, so it's x approaches -1 from the negative side, from the left. So, when x is close to -1 but a little bit smaller, I have to use the second formula, because x is smaller than -1. So the function is absolute value of x minus 2. Now what about this limit? When x is close to -1, x minus 2 is going to be close to -3, and then the absolute value of this is going to be close to 3. Now what about the limit itself? So the limit of the function is x approaches -1. What about this one? Does the function approach any value as x approaches -1? No, it approaches two values, two different values. 1 and 3 composed from different sides. So this thing does not exist, because 1 is not the same as 3. Okay, so see you on Monday, and these things are assignments.